Welcome back. We are essentially now starting off our fifth module, I think, the next module, a separate module at least, and which is on instability, rupture and dewetting of thin film. Broadly, it falls into the thin film instability and dewetting. Now, if we look at how much we have progressed, we had this discussion on introduction, some of the basic concepts we have talked about related to particularly surface tension and wetting. Then we have learned, in fact, spread over two modules 3 and 4, the patterning techniques, and we are following that photolithography is the third module and soft lithography is the fourth module. We had a reasonable discussion on atomic force microscope, which in fact is the fifth module, and now we move on actually to the sixth module, which is thin film instability and dewetting. Let us sort of quickly recap. In fact, if you look into the topic, a very interesting topic. It is a spontaneous instability, rupture and dewetting of a thin polymer film, but I have also written simultaneously liquid film. Let us try to figure out what we mean to say and when this issue of film instability comes into picture. We need certain concepts, and some of those we have already had made some concepts. One of those concepts that we will be needing is the concept of spreading coefficient, and we all know the expression of spreading coefficient, and see even in front of you I also prefer to sort of write it down instead of trying to remember it. So, you have had a substrate, you have now coated it with a liquid. Therefore, you have a liquid substrate interface where the interfacial energy is gamma SL, and you have the liquid surface tension. So, SSL or SS21, as one can see, is essentially this. And now you understand a lot on surface energy and things like that. Let us see what a positive value and a negative value would imply. A positive value implies that in fact, by way of coating this film, you have reduced the total energy penalty, and therefore, this film is going to be stable, because this formation of this film is sort of a natural process, like the formation, an example of which is the formation of the native oxide layer on a pure silicon substrate, because silicon has very high surface energy, and with the formation of the oxide layer now the surface energy drops. Negative value, what would mean is that by way of coating a surface, you have in fact increased the total energy, and therefore, thermodynamically the formation of the film is not favored. Question to ask is then what would it imply? It would essentially imply that this particular liquid, which has to a film with negative SSL, in fact, what can you conclude? In fact, what you should conclude is in fact partially wets the substrate. It does not wet fully, right? It actually wants to form a finite contact angle, and you are forcing it by some means, and you also know now what is that some means, how you can do that. Some means by which you would get a film, continuous film of a partially wetting liquid. You know the technique how you can do that by spin coating. In fact, you supply excess amount of energy in the form of centripetal force, which sort of overcomes the balance at the contact line, forces the liquid to spread, right. You can of course create this, but typically we have seen in the context of photolithography that you form a film of a photoresist layer, that is a polymer. You can in fact create a film of any polymer by spin coating, and there is a catch. Issue is that if you take a pure liquid, there are going to be two problems in spin coating. So spin coating with a pure liquid on a non-wettable substrate. Problems are, if you take something like an organic solvent, this liquid will tend to, it will spread, no doubt. I mean, initially you have dispensed it on a surface, it is making a finite contact angle, you start spin coating, but if the vapor pressure of the liquid is high, what will happen is the liquid will start to very rapidly evaporate, and the rate of evaporation will essentially enhance as you spread the liquid, because the surface area goes up. Therefore, after a few seconds or maybe a few minutes, you will be not left with anything. So no question, the liquid had spread, like if you take toluene, chloroform, acetone, whatever you can take, the liquid had definitely spread even on a non-wettable surface, but you cannot do any time resolved experiments. You cannot do any experiments because the liquid has simply evaporated away. On the other hand, if you take something like water that evaporates very slowly, the problem is that it will spread. So suppose you have taken water, you now turn, it makes a finite contact angle, which water in fact makes on most surfaces, because water itself is a pretty high surface energy liquid. So it does not that easily wet a surface. You spread it, it spreads, you rotate it, it spreads, but it does not evaporate. So it remains in its low viscous state. Now you turn off your rotation, the problem is water is going to retract back or dewet into its original configuration. So you again cannot get a permanent film, but with what type of material you can get a permanent film, and that is why this polymer becomes a wonderful model system for this type of study. Because what you do, you take a dilute solution in an organic solvent, let us say, which is rapidly evaporating solvent, you spin coat, it spreads, solvent evaporates. So here is the footprint of the solvent now during spin coating. You have the solute, the solvent evaporates away, and the solute gets deposited on the surface. So you get a film on a non-wettable surface which remains. So that allows you to make some experiments. The second thing is what is going to come up, where you will again realize the utility of having a polymer, and also the implication of using these two words in the heading is the form of spontaneous instability and rupture we are going to talk about in fact requires a liquid. But again the same problem, I mean, if you really do the experiment with a highly volatile organic liquid, your characterization becomes very difficult, because what you see the film to be the film disappearing, but whether the film is disappearing due to rupture, instability or evaporation, you cannot deconvolute. So the trick is that you take a polymer film, when you want to see the instability and the dynamics, you take the polymer in a liquid form, and you can very easily do that. We have already learned that. You take a glassy polymer, simply heat it beyond its glass transition temperature, viscosity reduces by many folds, so it behaves like a liquid. You have all the evolution there, we will soon see examples, and then at whatever stage you want to characterize, you simply cool down the temperature, just the way you have frozen the structures in nanoimprint lithography, and you get permanent structures, right. The other advantage is that most polymers have long chains, so the molecular weight is high, therefore the viscosity is high, and therefore the dynamics is slow. So that allows you to sort of track the evolution on minutes or on realistic time scale. Sometimes it can be even slower, in fact. So these are some of the advantages of using a polymer. But anyway, we are talking about the basic concept. So we have this spreading coefficient, that's an important criteria, but reality is that we often see water stored in a plastic bucket. Plastic is reasonably hydrophobic and it does not prefer to have water, but then the water layer it does not rupture, right. Why? Because you have adequate thickness, and therefore the I mean sort of the even though locally the spreading coefficient is negative, nothing matters, because there is too much inertia or too much amount of material present, and no instability is manifested. That also brings us to one unanswered question so far: what leads to the manifestation of this instability? And to answer to that, or to initiate a discussion on that, I would like to remind you of what we have talked about VDW forces. Something that I have not yet talked, and is how the scaling changes between two surfaces. That is something that is coming up in the immediate next lecture. What we know from the 612 potential or the LJ potential is that the scaling of the interaction forces is, the attractive part is r to the power 6, and we have also argued that roughly this separation distance is of the order of 10 nanometer. Well, here comes the question. So, this is between two fundamental particles which we have been talking, considering the hard sphere model. This is the separation distance. What is hard sphere? I mean, this is in fact the point where the outer orbitals of the two molecules come in contact, and beyond that, if they, I mean, so r equal to 0 is essentially when the two nuclei coincide, and that happens only in a nuclear reaction, nuclear fission reaction in fact. Other than that, what happens is, as soon as the molecules come too close to each other, their orbitals starts to overlap, and therefore you get this strong electrostatic repulsion between the electrons. But what we are asking is, what happens when you consider the interaction between two surfaces which are very close to each other. I have mentioned qualitatively, and for the time being, please believe me, we will soon see it mathematically, that the scaling in fact changes to 1 by r square or d squared, where d is the separation distance between the two. It does not remain r to the power minus 6, it becomes d to the power or r to the power minus 2. So, what is the consequence? Consequence is, you can yourself understand that this tail becomes much, the slope becomes much relaxed, or the decay characteristic becomes much sluggish, or in other words, the interaction becomes longer range as compared to that between two fundamental particles. And this is indeed true, this that there arguably this is sort of the order of 100 nanometer. People have their doubts, but maybe it is 50 nanometer, but it is certainly more than 10 nanometer. It is something more like 40, 50, 60 nanometer, something like that. There is active van der Waals interaction, right. So, this is another thing that one needs to understand, and therefore, again when we are back to a thin film, so if the film thickness is greater than, let us say, this 100 nanometer, for the sake of argument we are assuming this 100 nanometer to be the cutoff. Now, when let us say the film thickness is thicker than 100 nanometer, what does this picture tell you? That there is no interfaces of the film. Fair enough. So, in our context, in fact, this is a thick film. I very first day itself I emphasized that we will consider something to be a thin film if there is active interfacial interaction between the two interfaces. That is not there, so it does not really matter. The film can still rupture, you may not have a uniform film, because if there are some surface defects or something like that, but even if the spreading coefficient is negative, that from the standpoint of a spreading coefficient you see that this film is unstable, but van der Waals force is not going to cause any damage to the film stability. However, if the film thickness is now, and H we are marking as film thickness, what does it say? Does it immediately tell, oh, well, this is a condition for film instability? Please do not jump onto conclusion. All it tells, now you have active van der Waals interaction between the two interfaces of the film. Fair enough. You may still ask, so what? One quick answer would be, so there might be certain things. Now it depends. We have told the interaction is active. We haven't mentioned whether the nature of the interaction is attractive or repulsive. In fact, you will see that the sign of the spreading coefficient in fact tells you whether the nature of the interaction is attractive or repulsive. It sounds a bit surprising, because so far we have always been talking van der Waals interaction to be attractive, and now suddenly I am telling, well, the interaction may be attractive, may be repulsive. We will see that it in fact depends on certain relative magnitudes of something called Hamarker constant of the film and the surface, which we will discuss soon. Suppose this interaction is attractive, which you are expecting, because van der Waals interaction is attractive. So the surface in fact pulls this interface, but there is liquid. So what will happen? Does it sort of merge and the liquid squeezes out, like what we have seen in the, let's say in the case of colloidal, two colloidal particles joining up? It's not like that. In order to understand what happens, and this is a absolutely qualitative discussion I would like to trigger deliberately, we will add some scientific and mathematical terms, but this is a deep understanding that you need to develop, and the understanding is pretty qualitative. Let us see what we can do. In order to progress, we need to sort of look into again a layer of stagnant liquid, let us say water, which is stagnant. Fair enough. So this can be, let us say, a bucket full of water. If I ask you that there is no external force and there is no flow, there is no leakage, what would you expect the condition at the interface, the liquid air interface? And immediately all of you will say there is a stagnant liquid. So u, v, w, the three components of velocity at the interface are all 0, which is very logical, is a perfectly valid macroscopic picture. But now suppose I give you a hypothetical tool to sort of examine this interface at let us say a 10 nanometer resolution. And why I say it is a hypothetical tool, because do not confuse, AFM cannot examine this, because AFM is capable of only examining a solid sample, not a liquid sample. It can analyze a sample under liquid. I did not highlight that, but there is something which was mentioned as liquid cell. But suppose if you sort of are allowed to examine this interface, which is apparently static, apparently flat, everything at, let us say, a very high magnification, and at very high you are allowed to acquire data at very high time frequency also. What would you see? You would in fact see that there are some very high frequency fluctuations which are also very low amplitude, few nanometer. What is the genesis of this fluctuation? Well, this fluctuation, it sounds very surprising, but these fluctuations are there and there is no damage to the interface. So a bucket full of water, a cup of coffee, whatever, whenever you see a stagnant free surface, in fact there is some very high frequency fluctuation like what is drawn here, right? It is high frequency, low amplitude. What is low? Few nanometers maybe. So what is the genesis of this fluctuation? Well, these fluctuations are attributed to the internal kinetic energy of the molecules. You remember, every material has some internal energy, and this internal energy in fact has several components, like internal potential energy, which is essentially the interaction forces like van der Waals forces, internal kinetic energy, there can be vibration, etc., also, but this is attributed to the internal kinetic energy of the molecules, which is numerically presented as Kb into T. Now you see T is absolute temperature, and you are, let us say, looking at a bucket at room temperature, or you are looking at a polymer film which is elevated, which is heated beyond its glass transition temperature. So T is non-zero, Kb anyway is non-zero, so this term is non-zero always, right. So the molecules in fact try to go away with each other, and surface tension or the interaction forces bind them together. So, there is a competition that goes on, right, and this leads to this type of fluctuations. So, in other words, these fluctuations are omnipresent. Unless you are performing your experiment at absolute 0, of course, then T is equal to 0 and this fluctuation goes away. Now, you have a liquid surface, and which you understand is not flat. Consequence, curved liquid surface, what is the thing we have learned? There is Laplace pressure. Why? Because let us say if you look into this segment of the film, and you know between the 2 points 1 and 2, the lowest length segment will be if the film surface is flat. That corresponds to the lowest energy, lowest surface energy configuration. So, the moment there are these fluctuations due to the internal kinetic energy or oscillation of the molecules, in fact, it increases the surface tension, and surface tension, it increases the surface energy, and surface tension opposes this growth. Or in other words, what happens, you can go one step deeper and try to explain it. In fact, there is Laplace pressure, and you can sort of write Young Laplace equation. We just take an exaggerated view of one single oscillation. Here this is going to be R1, here let us say this is going to be R12, this is R11, and you can yourself see in fact that if this is positive, this is going to be negative, right. So, the Laplace pressure PL1, assuming it is exposed to atmosphere, so the outside pressure at both the places is same, PL1 is going to be greater than PL2, and this is something I briefly mentioned while I was talking about Laplace pressure. So, we all know that liquid flows from high pressure region to low pressure region. So, what happens now? Liquid simply flows from this area to this area, and therefore, the meniscus flattens out. So, there is a dynamic competition that goes on. It is a dynamic steady state. Fluctuation, flattening, and so on. So, however counterintuitive it may sound, but if you look at a flat liquid surface, you now understand that there is at the nanoscale there is some fluctuation going on continuously, right. So, what I mean, it is fine. So, a bucket full of water, there is fluctuation, this amplitude is few nanometers, maybe, even if it is few nanometer, nobody knows, nobody has visualized it so far till date. But now you start thinking of a thin film, thin liquid film, like the ones we have considered here, right. So, this thin film, now you understand that at any time snapshot, it is actually like this. Let us say your film thickness was of the order of tens of nanometer, and this amplitude couple of nanometer, few nanometers, maybe 4 5 nanometer, and this is let us say 20 nanometer. So, for a 1 meter deep water level in a bucket of water, 2 nanometers nobody even cares, 9 orders smaller. But when your film thickness is 20 nanometer and let us say this amplitude is 4 nanometer, the amplitude, the oscillation amplitude is just 1 order lower, and in fact, it turns out that it can be 5 to 10% of the film thickness. Okay. So, this is very important, and now you, since the thickness, the overall thickness of the film is lower than 100 nanometer, you are talking of a regime where essentially there is active van der Waals interaction. So, in case now, and what is the case we will realize soon, the VDW interaction is attractive, and as I told, this interaction scales as 1 by d square, d is the separation distance. So, what happens is, this is let us say the mean film thickness, at any instance of time this is the fluctuation spectrum. So, what you now observe that at point 2 the VDW interaction is stronger, and remember the nature of the interaction is attractive. So, now what we have discussed here, the moment there is a fluctuation, the film would ideally flatten out, right, but here now you have an additional complexity. Since the attraction is stronger here and it is stronger at this point as compared to this one, these two are trying to come in contact with each other due to van der Waals interaction, or in other words the substrate is sort of pulling. Remember that this surface cannot go up because this is a rigid surface, rigid interface defined by the geometry of the substrate, but the liquid free surface is a deformable surface, and therefore, it wants to deform because it is feeling an attraction towards the surface due to van der Waals force, and this is what is called, again there is a flow. So, there has to be, so this if this amplitude grows, there has to be some flow, therefore, people term it in terms of some pressure. This is terms as the disjoining pressure, something again we will discuss. So, there is now an additional component, the van der Waals force driven disjoining pressure, which tries to pull the two interfaces, and Laplace pressure tries to flatten it out. So, now there is an additional competition. So, the moment there is an additional competition, now one needs to look at the relative magnitudes of the Laplace pressure and the disjoining pressure. I will stop here, let these ideas settle in your head. I will show a video as to what happens, and then we need, for a good understanding of the situation, we need a real good understanding of the disjoining pressure, which is something that I will take up in my next lecture. Thank you.